This episode, we are going to analyze the deflected shape of a simply supported beam with a point load which is eccentric. So this point load is at a distance A from the left support and at a distance B from the right support. And in this problem, we are going to consider the case where B is greater than A. Obviously, either A is greater than B or B is greater than A. Doesn't really matter. But let's say in this case, B is greater than A, and intuitively, that means that the maximum deflection is going to be between these 2 points. Right? Think about that for a little bit, but it has to be that way. But we're going to do the math and we're going to prove it. So first of all, let's remember that the shear diagram for this looks like this, like that. And these two reactions here are PB over L, and here PA over L. And the moment diagram for this looks like that. Right? These are both straight lines. If we look at the moment diagram, cutting here and looking from here and calling that X, that equation becomes PBX divided by L, right? And if we look at the moment diagram this way, we call this X prime, then the moment diagram as a function of X prime looks like PAX prime divided by L. So they're both straight lines. If we start from both ends, they are very simple. It's just a constant times X. The reason we're doing this is that it'll be very convenient when we're trying to solve the equations to basically use compatibility, looking at the deflected shape coming from both sides. So let's go ahead and do that. Let's just draw it out intuitively, just to have a sense of how these deflected shapes would look. It looks something like that. The maximum will be at this side, and then something like that. The maximum deflection would most likely be somewhere here. And at that point, the slope of the deflected shape is 0. But the moment equations change at this point. So if we come from the left to the load, we find that, as I said, M, the function of X, would be PB times X divided by L. The slope would be PBX squared divided by 2L plus a constant. And the deflected shape, right, all of that times EI, then again EI times Y would be PBX cubed divided by 6L plus 6(1) times X plus C2. Now from this equation here, we realize that when X equals to 0, Y is 0. So that means that C2 is 0. Now, if we look at the moment equation coming from the right to the load, the moment mx prime looks like PAX prime L, EI times the slope looks like PAX prime square divided by 2L plus C3, and EI times the deflection looks like PAX prime cubed divided by 6L plus C3X plus C4. Again, when X prime equals to 0, Y is 0, which means that C4 equals to 0. And so here comes the basic step in order for us to move forward. And basically the reason why we've written the moment equations in this way, one coming from this way and one coming from that way, is that we are going to invoke compatibility at this point. Basically, when X equals to A and X prime equals to B, the deflections have to be the same and the slopes have to be the same, although one of them will have an opposite sign, right? Because this one is already turned while this one is still going down. But in value, they will be the same. We do have to account for the sign difference in the angle. So we'll start by equating this equation to that equation. So we'll do that over here. Basically that means PB A square over L over the 2L, right? Plus C1 equals to minus PAB square over 2L minus C3. Again, this equals to this with a negative sign because the slope has already turned at that point, because it has already gone through the maximum. So if we do that, we obtain an equation that relates the two C's, right? So we get this by equating these two, and now we are going to equate these two, right? This is the vertical deflection. This equals to that. In this case, we don't have to change the sign because in both cases the deflection is downward, obviously. So we're going to have this other equation which says that P B A cubed divided by 6L plus C1 times A equals to P A B cubed over 6L plus C3 times B. Okay? So we have here two equations with two unknowns, C1 and C3. In order to solve these equations, basically what we're going to do is we are going to multiply this top equation by A, get these two terms the same, and then we're going to multiply this equation by -1, and then when we add them up, this term C1A will cancel and we're just going to be left with C3. So if we do that, this is what we obtain. Again, we multiply this whole equation by A, and we multiply this whole equation by -1. And then we add them up, right? So we obtain this result. P B A cubed divided by 3L. Basically, that is this term, PB A cubed, right? So it's 1/2 minus 1/6. You get 1/3. That equals minus PA square B square over 2L minus PAB cubed divided by 6L erase this part here. So again, that's this PA square B square over 2L negative minus PA B cubed over 6 minus A times C3 minus B times C3. So we take these terms, bring them to this side, and solve. So we get PBA cubed over 3L plus PA square B square over 2L plus PAB cubed over 6L equals to minus A times L. Because here we have A plus B. Sorry, this is C3. C3 times L, because A plus B is L, right? So from here we can solve for C3 by simply dividing. We got a minus and then we get an L square down here. Right? So that's C3. And now, this is what we do. We know that the maximum is on this side. In order to find the location of the maximum, right, we're going to call that X star. In order to find X star, we put that C3 in here and we solve for X when this side is 0, right? Basically, we take that, take this C3, put it in here, and solve for X when the slope is 0. And if you do that, what you find after a little mathematical manipulation is that X star is equal to square root of B times 2A plus B divided by 3. You can write this in another way if you want. You can say, you know, A plus B is L, and then you have L plus A times B. Doesn't matter, but basically this is the result for X star. This is the result for C3. And so if you want to find the maximum deformation, you take this C3, you put it in here, and you evaluate this equation at this point, and that will give you the maximum deflection delta on the beam. Okay? So this is again a case where you have to use compatibility, and you have to be careful to realize that these angles are the same but with opposite signs at the point where you have to use compatibility in order to find the integration constants.